Welcome to G Fun Facts Online. Today we are diving deep into the invisible machinery of our planet's water cycle to understand a crisis that is redefining modern civilization. We are talking about Day Zero. This concept was once the stuff of dystopian fiction, a scenario where a major metropolis, a hub of commerce and culture, suddenly turns off the taps. But on a sweltering day in 2018, the residents of Cape Town, South Africa, stared that reality in the face. They called it Day Zero, the calculated date when the city's reservoirs would drop below 13.5% capacity, forcing the municipal water supply to shut down. Had this occurred, residents would have been left to queue for a daily ration of just 25 liters, or 6.6 gallons per person, under the watchful eye of the military. Cape Town narrowly averted that disaster through a combination of desperate conservation and lucky rains, but the term Day Zero entered the global lexicon. It became a shorthand for a terrifying new reality where water scarcity is no longer just a problem for arid outposts or rural villages, it is coming for the world's megacities. As we move deeper into the 21st century, the hydrological stability that underpinned the rise of modern civilization is fracturing. In 2019, Chennai, India, one of the world's wettest major cities, saw its taps run dry, forcing millions to rely on water tankers. In 2024, Mexico City teetered on the brink with reservoirs at historic lows, and in 2025, warnings are flashing red across the Mediterranean, Southern Africa, and parts of North America. This crisis is not merely a result of bad weather, it is a collision of three titanic forces. First, anthropogenic climate change is supercharging the water cycle. Second, explosive urbanization is concentrating thirst in concrete jungles. And third, antiquated water management is often flying blind into a future it cannot predict. To survive this future, we need more than just concrete dams and desalination plants. We need a digital revolution in how we understand water. We need to see the invisible flows beneath our feet and the atmospheric rivers above our heads. We need hydrological modeling. This is the story of how scientists, engineers, and data wizards are racing to build a digital nervous system for the planet's water. To predict Day Zero, we must first understand the science of scarcity. Day Zero is technically a system failure. It is the moment when the buffer in a hydrological system, such as reservoirs, aquifers, or snowpack, is exhausted by the load, which includes human consumption, evaporation, and environmental flow requirements. In a stable climate, calculating this buffer is standard engineering. You look at historical rainfall records, calculate the safe yield of a dam, and plan accordingly. But we no longer live in a stable climate. We live in a world of non-stationarity. This is a critical hydrological concept, meaning that the past is no longer a reliable guide to the future. To model drought today, you must first model heat, because the period of 2024 to 2025 has been the warmest on record, and heat is a thief. It steals water through evapotranspiration, the combined process of water evaporating from soil and transpiring from plants. For every degree Celsius of warming, the atmosphere can hold about 7% more moisture. This turns the atmosphere into a giant sponge. Before rain can fall and fill a river, that atmospheric sponge must be saturated. In a warming world, the sponge gets bigger and thirstier. This leads to a phenomenon seen clearly in Australia's Millennium Drought and the recent Colorado River crisis, known as declining runoff efficiency. Historically, if you had 100 millimeters of rain, you might expect 30 millimeters to reach the river. Today, in parched catchments, that same 100 millimeters might yield only 5 millimeters of runoff, because the thirsty soil and hungry air drink the first 95 millimeters. Old hydrological models, calibrated on 20th century data, often miss this. They predict reservoirs will fill, but the water never arrives. To accurately predict Day Zero, modelers must track a drought as it shapeshifts through four distinct stages. First is meteorological drought, the deficit of rainfall tracked by satellites. Second is agricultural drought, where soil moisture drops and plants become stressed. Third is hydrological drought, the deficit in stream flow and reservoir levels, which is a slow-moving disaster. Finally, there is socio-economic drought. This is the crisis point, where physical shortage meets human demand. Traditional hydrology focused heavily on the first three stages, but the revolution in modern modeling is the integration of the fourth stage, the human element. Predicting this complex future requires a diverse arsenal of digital tools. At the foundation of hydrological science are physically based models, or PBMs. These are complex software engines that solve the fundamental laws of physics, such as conservation of mass and thermodynamics, across a landscape. Famous examples include the Soil and Water Assessment Tool, known as SWOT, and HECHMS. These models divide a watershed into thousands of tiny grid cells. For each cell, they calculate how rain hits the canopy, drips to the soil, infiltrates the pores, and flows downhill. Their strength is transparency. If the model says there is no water, you can look at the equations and see exactly where it went. However, they are data-hungry monsters that need precise maps of soil types and topography. If your map is wrong, your prediction is wrong. In the last decade, a new player has entered the field: artificial intelligence. Unlike physical models, AI doesn't necessarily know that gravity pulls water downhill. It simply looks for patterns in massive datasets. Algorithms like long short-term memory, or LSTM networks, are proving uncannily accurate at predicting stream flow. You feed the AI 30 years of rainfall and river level data, and it learns the relationship between the two. But pure AI can be dangerous. It might predict physically impossible things, like a river creating water out of nothing. The cutting edge today is physics-informed machine learning, or PIML. This technology embeds physical laws into the AI's learning process. The AI is punished during training if it violates laws like the conservation of mass. In recent case studies, such as on the Gidra River and in experiments by the USGS, these models have outperformed traditional physical models, especially in areas where we lack detailed soil maps. But you cannot model what you cannot measure. For decades, hydrology was limited by the number of rain gauges a country could afford. Today, satellites fill the void. The GRACE satellites, or Gravity Recovery and Climate Experiment, allow us to weigh groundwater aquifers from space. They measure subtle changes in the planet's gravity field caused by the movement of water mass, revealing depletion in places like California's Central Valley and northern India. NASA's SMAP satellite measures moisture in the top 5 centimeters of soil globally every 2 to 3 days, providing critical initial conditions for drought models. Perhaps the most important innovation is sociohydrology, which models the human feedback loop. Traditional models treated humans as a static straw sucking water out of the river. But humans are dynamic. When a drought forecast is issued, people change their behavior. They might panic buy water, increasing demand, or adopt strict conservation. Conversely, if a model predicts a wet year, farmers might plant thirstier crops, paradoxically increasing vulnerability if the model is wrong. This is known as the reservoir effect, or the Jevons paradox. Agent-based models are now used to simulate this, populating virtual cities with thousands of agents to see how different neighborhoods respond to rationing. The culmination of all these technologies is the digital twin. A digital twin is a living, breathing, virtual replica of a city's entire water system, connected in real time to the physical world via the Internet of Things. Imagine a control room in Valencia, Spain, home to one of the world's most advanced water digital twins. Thousands of sensors measure flow, pressure, and quality every second. A hydraulic model runs in the cloud, constantly calibrating itself. It allows utility managers to fast forward into a drought. They can ask, if we lower the pressure in the pipes by 10% at night, how much water do we save? In Mexico City, where 40% of water is lost to leaks, digital twins analyze pressure waves to pinpoint leaks within meters, allowing for surgical repairs. Hydrological modeling has allowed scientists to map the risk landscape of the next decade, and the results are sobering. A 2025 study identified that day-zero hotspots could emerge in 35% of drought-prone regions within the next 15 years. The Mediterranean basin is warming 20% faster than the global average. In 2024 and 2025, Catalonia faced its worst drought in centuries. Models predict an aridification trend, meaning the atmospheric sponge is drying out permanently. In Bangalore, India, known as the Silicon Valley of the East, the disconnect between urban planning and hydrology has led to severe crises. The city paved over its natural lakes, which acted as recharge zones. Models show that without a 60 to 70% reduction in groundwater extraction, the aquifers will functionally collapse. Even high-altitude cities are not safe. Bogotá, Colombia, and Quito, Ecuador, rely on Páramo ecosystems, natural water factories that capture moisture from clouds. In 2024, Bogotá began rationing water due to a combination of El Niño and ecosystem degradation. Models failed to predict the speed at which the Chingaza Reservoir emptied, highlighting the need for better soil moisture monitoring in the high Andes. In the Colorado River Basin, serving 40 million people in the western U.S. and Mexico, the Bureau of Reclamation uses the Colorado River Midterm Modeling System. They have shifted from deterministic forecasts to probabilistic forecasts, predicting 100 possible futures. This allows for trigger planning, where pre-agreed cuts kick in automatically when the model hits a certain probability of failure, removing politics from the decision. And politics is often the hardest part. Hydrologists face the false alarm dilemma. If a mayor rations water based on a model and it subsequently rains, they look like an alarmist. If they don't ration and the city runs dry, they are negligent. To solve this, we need better communication of uncertainty and economic innovations like Australia's water markets. During the Millennium Drought, Australia separated land rights from water rights and used models to determine a consumptive pool of available water that could be traded. This allowed water to flow to its highest economic value, saving agriculture from total collapse. We also see the rise of citizen science. The Kokora HS network allows regular people to upload rainfall data, which helps catch localized flash droughts that sparse official networks miss. The era of stationary water management is dead. We are flying into a storm, and our old maps are useless. But we have new instruments. The city of the future will be a sponge city, designed to absorb every drop of rain, monitored by a digital nervous system. Singapore captures every drop that falls on its island. Windhoek, Namibia, has been drinking recycled wastewater since 1968. Cape Town learned that consumption can be cut by 50% without destroying the economy if the communication is clear. Hydrological modeling gives us the foresight to see the cliff edge. Whether we hit the brakes or drive off, it is no longer a technological question. It is a political and moral one. The models are blinking red. Day zero is a choice. And the time to choose is now.